Distance vector protocols. Distance vector protocols were key in the development of early networks to include the ARPANET, which was a predecessor to what we now know as the Internet. In this nugget, we're going to look at the Bellman-Ford algorithm and see what its purpose is. And then we'll take a look at the metrics and understand how they're used to determine the best path through a network, followed by a look at updates and how they work. Then we'll take a look at the biggest problem facing routing protocols today, and that is routing loops. But I'm not going to leave you hanging. We're also going to talk about how distance vector protocols combat this problem in loop prevention. And then we'll end up with a discussion on load balancing, what it is and how it works. The Bellman-Ford algorithm was actually named after two individuals. First, Mr. Bellman, who developed the mathematical equation that serves as the basis for the algorithm, and then Mr. Ford, who used that equation in his works that included flows in networks. This paper, Flows in Networks, was actually used as a reference for the RFC that defined RIP, which was one of the first distance vector protocols. The purpose of the algorithm is simply stated as it needs to find the shortest path from one point in a network to another point. All right, this algorithm also is the basis for all distance vector routing protocols, not just RIP. It was used in the early days of the ARPANET as well, which is what preceded the Internet. So, all right, the question has to be asked then, how does it determine which path is the best? Let's say I'm starting on this side of the network and I want to end up in this network. I have options here. I could go this path or this path. What is it that keys this algorithm on which way I should go? You recall from earlier discussions that each router holds in it a routing table, and it was analogous to the directional signs if we were taking a road trip from Los Angeles to Dallas. Now, keeping that in mind, it wasn't the sign itself, the physical sign, that told us where to go. It was the information on the sign that said, okay, this route, let's say, is 900 miles, while this one is 1,800 miles. All right, decision easy. I'm going down the 900-mile path because it's shorter. Same holds true with the route tables. It's not the route table itself, but there's a piece of information on the route table that says one path is shorter than the other, and that is known as a metric. Now, distance vector routing protocols simply call for a metric to be used, but they don't define specifically which metric has to be used. So as you have different protocols within the distance vector category or type, you're going to have different metrics. Let's look at some examples. First, we have RIP version 1, and it uses hops. That's also known as, it's short actually, for handoff points. And usually that signifies every router as a handoff point along the path to your final destination. Now, if we're running IGRP as a protocol, it uses a composite metric. And simply that's just one way of saying there's a lot of pieces into this metric. They are bandwidth, delay, load, reliability, and MTU. And all of that is used to get a better picture of what is on that wire and how fast can I traverse the wire. So let's illustrate on our diagram how each of these metrics might be used. First of all, we're going to go with RIP. And we're going to do that on the inside of our diagram. Now keep in mind that distance vector protocols are known as routing by rumor. That is to say, I will have a network here that I want as a destination. This router will see that network as directly connected. So the metric to get there is 0. It's right in front of me. Now as it passes that update on to each of its neighbors, which are these two routers, they will have to increment that metric by 1 because they have one handoff point apiece to get to this network. This router has to go to this router and then the network. And then it just increases from there. 2 handoff points before it gets to the network from that router. Now this router, this is where it gets interesting. Depending on the path it takes. So if it takes the path this way, it's actually 3 handoff points to get to this network. If it goes this way, it's 2. All right, pretty simple, right? So when we look at the routing table, if we're using RIP version 1, it's a pretty easy decision. We go down this path here because it's 2 hops away rather than 3. It doesn't take into account what's really happening on the wire. It's kind of a real-time analysis, and that's where IGRP comes in. With this composite, it looks at the bandwidth available, it looks at the delay across that network, looks at the maximum transmission unit, all these pieces put together, and then it says, I'm going to go over this path. So let's see if we differ the bandwidth on each of these legs, what might happen. All right, before we do that though, let's annotate down here the paths that we had in this router in our route table. So R1 is what we're going to label this one. All right, for RIP we had a route of 3 hops in one direction, 2 in the other, so we opted for the lower route. All right, moving on to IGRP, let's say that this link now is 56K, this is 56K, this is a T1, this is a T1, and this is a T1. All right, what we're not going to be able to do is illustrate the whole composite. I can't work out the metric for delay within this diagram, but keep in mind that it would do that. What we do need to understand, though, is that a 56K circuit in comparison to a T1, T1s are about 27 times faster, all right? So it's going to draw our point home. All right, if I use IGRP and I run my composite metric here, I'm going to come up with a number, and I'm going to pull a number out of the air for the sake of our discussions. Let's say that a 56K link comes up to 30 as a metric. Same here, I get 30 as well. And let's say here that I get a metric on a T1 link of 10 because it's much faster. 10 on this link and 10 on this link. Well, adding up my metrics on the initial path here at the top, I have a metric under IGRP, a total metric because they're cumulative, of 30. Now adding these two routes up together, I have a cumulative metric of 60. So now, even though I only have one router in between me, or actually two, and the destination, and here I have 3, the shorter path is here because I get a real-time analysis with IGRP of what's happening on that network, and I take bandwidth into account. Pretty cool, huh? Now, I mean, that could be true the other way around. These could have been 56K links. These could have been T1, and it could have been that RIP and IGRP would still agree on the optimal path. Distance vector routing protocols are designed for medium to small size networks. They can't handle very complex, large networks. And so to guard against that happening by mistake, the authors of RIP and IGRP came up with an idea called infinity. Now, in reference to a metric, this is what it means. For RIP, 15 hops are allowed between a source and a specific destination. As soon as you get to that 16th hop, it's considered infinity. The number's not as important as the idea. It's simply saying, if in your route table you have a metric of 16, that network to you is unreachable. Now for IGRP, infinity equals over 4 billion. Again, it's 2 to the 32nd power. But again, the number's not as important as the idea of infinity. It's simply saying that network is unreachable to you. So it seems as though, as far as calculating metrics here at R1 and trying to get to a destination, it's simply a math problem. We add the metrics associated with this path, we add the metrics associated with this path, regardless of whether it's RIP or IGRP, and we come up with the best path. The question has to be, though, how does R1 know the metric associated with this link, and this link? And the answer to that comes in the form of an update. An update is information that's passed from one router to the other with the idea of finding the best path. Updates within the distance vector routing protocols are defined as periodic. Now what does that mean? That means that at a predetermined length of time, it's going to send a route update from this router to every neighbor. And that's going to be true for every router. All right? So that's going to be a different time in RIP than it is in IGRP. In fact, the default in RIP is 30 seconds, where IGRP is 90 seconds. Every 90 seconds or every 30 seconds, the complete route table is sent out, whether there were changes in the network or not. All right, now there's nothing that mandates that all these routers within one routing environment, let's say they're all routing RIP, have to have the same timer associated with its updates. But there'll be very, very bad consequences if you don't. So many that we can't even describe them all in this scope, and some things that probably nobody's ever seen. You can't have a route update timer of 45 here, 60 here, 90 here, and 30 here, all within the same routing algorithm without asking for trouble. Now, another key thing to understand about updates is, as I send it from this router to this router, there is no acknowledgement coming back. It's sent via UDP, which if you remember from our earlier discussions on the OSI model, UDP is connectionless. So it's just sent out, best effort, and it hopes that it gets there. And it relies on this network being in good enough condition to get it there. The reason for that decision is not just a matter of the thinking that these networks were always reliable, so the information will get there. It's followed up on another 30 seconds or another 90 seconds by another update. So it feels that if it was lost, it's okay. And one of the main goals in designing the distance vector protocol was to save on bandwidth and overhead. So they didn't want TCP setting up a three-way handshake, sending the information, and then have the information get acknowledged. It was just too much overhead. Keeping that in mind, distance vector protocols also call for broadcast traffic to be sent out. So they want to broadcast whenever they're sending their updates to each neighbor going out. It's interesting to note, though, that after distance vector and we moved into link state or even the hybrid protocols, instead of broadcast, MCAST were used. And that's because broadcast was used to save overhead and not have a unicast packet here and then another unicast packet sent here and it going out to each neighbor with a unicast packet. But what was found is with broadcast, it sent it to every router on the network. And it might be that this router isn't routing RIP as this router and this router are. So instead of broadcast, it's multicast. So they send out with an address that says, if you see it, don't process it. If you see it, you're part of my multicast group. Go ahead and process and use it in your route table. These periodic updates are great updates on networks that don't change much. But you got to understand, you realize, I'm sure, there's not many networks out there that just don't change. So they had to come up with a second type of update. We have the periodic, and then we also have the triggered update that will address when a network goes down. So let's say that this network goes down. As soon as it goes down, instead of waiting till the next periodic update, which if one just went out, it could be as long as 29 seconds or as long as 89 seconds, it's going to have a triggered update. And what that means is it's going to send out an update immediately, as soon as that happens, to all its neighbor routers. Now understand, a triggered update is because of a change in state, not because of a change in metric. So if I have a route table that says to get to this network, and let's just label it Y. Let's say to get to network Y, it's directly connected, so I have a metric of 0. If something comes up and that metric changes to 1 or 2 or any other number, that's not a change in state, that's just a change in metric. What I'm looking for is a change from the state of it being up to the state of it being down. As soon as that happens, that's when I send my triggered update to everybody. And that cascades to the network, because as soon as you receive one here, this router is going to send it out to each of its neighbors, and it's going to go out quickly. And the idea there is to get quick convergence. And remember, convergence from our earlier discussions is when every router on a network has the same understanding of that network, and it's a true understanding. So these triggered updates allow for quicker convergence than it would if we waited for RIP, version 1, or IGRP to send out its periodic updates. All right, so that's our safeguard if a network goes down. And because there's still connectivity here, the router can report that. But let's go to another scenario. What if this router goes down completely? Now, there's nobody to report it up the chain, right? There is no hello timer here that says, you know, every X number of seconds, hey, I'm here, I'm here, I'm here, so that when you lose that, you can say, hey, this router's not here anymore. What happens is there's a timer on each of these routers that says if I don't get 3 consecutive updates, I'm going to take every route that I learned from this router and delete it out of my route table. Just take it right out because it's not trustworthy any longer. Now, if you miss 2 and it comes back on the 3rd, everything will be fine. It has to be 3 consecutive updates that are missed. A key note here is you got to remember a second in network time is actually a very long time. So if we're talking about 3 consecutive updates before I make changes to my table, I'm talking with RIP 90 seconds. I'm talking with IGRP 270 seconds. That's a lifetime in network time that I'll have these routes in here existing saying I can process traffic out that interface. So you see the necessity of triggered updates. Without them, we'd have a lot of downtime within our networks. All right, so far in this nugget, we looked at Bellman-Ford and its purpose and how it defines distance vector protocols as an algorithm. We also looked at metrics and how their job is to tell you which path is the optimal path to run down. And then we looked at updates, how metrics are passed from one router to another. The next thing we're going to look at is routing loops. It's one of the biggest problems facing distance vector protocols. The anatomy of routing loops is mildly complex. And you might even think once we illustrate it that it won't happen that often, but it does, and that's why we have to have loop prevention. So let's look at what we have. First of all, our network diagram. I have 3 routers, R1, R2, R3, and I have a network hanging off here, a network of X. And we're going to use that in our stages. These are going to be the steps that happen in the network, and as we run through the stages of that network diagram, we're also going to look at the routing tables and how they affect R1, R2, and R3 at each stage. So as the first step happens, here's the results of the routing table for that step. The second step, here's the results, and so on. All right, let's dive in. Here's our first step. R3, which is this router, is going to send a routing update. That's what my arrow indicates. And that routing update is going to say, to get to network X, it's 1 hop away, so here's the metric, and it's going to send it to R1 and R2. If it's RIP, remember it's broadcast to both of them. If it's IGRP, it's a multicast, hoping that both of them are running the IGRP protocol. All right, so the result of this update is going to be R1 with a route table that says to get to network X, remember network X is the only line we're dealing with here. To get to network X, it takes 1 hop count, so this is the metric, and it's via R3. Go through R3 to get there. Same thing for router 2, and then router 3 is going to say, my metric is actually 0 because it's directly connected. Okay, the next step is important here. The network X changes state. Remember, not a change of metric, but a change of state. So this network just went down. It's unreachable from R3. The first thing R3 is going to do is send a triggered update out of its interfaces to both of its neighbors. Now in this update, it's going to have information about other routes off of that network, but it's not going to have anything in reference to network X. And because of that, the result on the route table is going to be nothing in each of the route tables for network X. Now the key to the routing loop happening and where the complexity comes in is identified in these brackets here. This triggered update that went out on this wire a fraction of a second before step 3 happened, where R2, which is this router, sent out a report that to get to network X, it takes 2 hops, and it sent it to R1 and R3. Both of these routers saying to get to X, you come through me, then there's another hop and you get there. It's kind of a lie to R3, and we're going to look at safeguards against this, but it's telling R3, come to me, there's one other hop, and then you get to the network. All right? But the key point here is to understand that these 2 packets actually cross on the wire. There's another one going in this direction, there's this here. So this router sends these 2 out, this router sends these 2. Here we have a cross on the wire. As soon as R2 receives this update, R3 is going to receive what R2 sent out, and it's saying that to get to network X, there's 2 hops. All right, so the result after the third entry here is accepted by R1 and R3 is going to be R1's route table, which is this router, saying to get to network X, I have 2 hops, and I go through R2. Now the reason it accepted that is over here it had no entry at all. Remember, that triggered update said, hey, it doesn't exist any longer, but then R2 comes and saves the day and says, you know what, actually it does exist and I know how to get there. So it updated the table. R2 doesn't receive anything on this. It was the one sending the 2 updates out. R3 receives that same update, and in his table is going to say, yeah, 2 hops away, I use R2 to get there. See, these routers, they're not as smart as we think in some instances, because, I mean, look at a scenario. There's some times that you might have this network interface shut down, and you'll activate it on another portion of the network. I mean, that happens, right? So it needs to be able to accommodate for that. So it's not a rare instance that this guy would say, you know what, I lost my connectivity to a network, and shortly after, another router said, hey, I've got that network hanging off of me. Like I said earlier, this crossing of paths on the same wire might sound unlikely to you and like it doesn't happen that often, but indeed it does, and there are much more complex causes of routing loops that we can't discuss within this forum. We just simply want to let you understand what a routing loop is and one of the causes. All right, let's move on to step 4. Once this happens, R1 is going to send out an update that says to get to network X, I have 3 hops to go, and I send it out to R2 and R3. The reason for that is these routers are doing just as they should. When a network comes, an update comes out of R3 to R2 saying that network X is 1 hop away, if the network was static, if we didn't have this problem, it would be expected to pass on to this router saying, come through me 2 hops and you get to that network. And then this router is expected to pass on, come through me 3 hops away, you get to that network, because there may be another router here. And so it tells all its neighbors, not only this entry and this entry, but also this guy. All right, so this packet is sent out, and the result of that packet is going to be route tables on R1 saying exactly what it said before. No change because it didn't receive a packet. It was sending packets out. Okay? The result on R2, hey, well, I had no route to that network. Now R1 says 3 hops away by sending it to me, and we can get there. So he changes his entry, and then R3 receives the entry that he sent out saying 3 hops away. It's not actually going to change it to 3 hops away through R1 because it has a better metric in existence, right here. So it's actually going to keep 2 hops away through R2. All right, so that's a routing loop. Now let's look at how we battle against that. The first defense against routing loops within the distance vector protocol is called split horizon, right here. Simply stated, it's omitting routes learned from one neighbor and updates that are sent to that neighbor. So if R3 sends an update to R2 about network X, when R2 sends its updates, it's not going to send it back to R3. It's going to omit information about a specific route that it learned from that neighbor. So it's just going to send it out this way. Let's see that in action. Here we have R3, as we did before, and its first step, it's going to send an update out that says to get to network X, it's 1 hop away, and it's going to send it to R1 and R2, both of these routers. So here we have exactly what we had before. 1 hop through R3 for both those 2 entries and directly connected here. All right, we have the changes we did. This network goes down, and now there's going to be a triggered update sent here at step 2. This triggered update is going to omit any reference to network X in that update. So the result, Just as it was in the whiteboard before, I have no entry to get to network X in any of my routing tables. All right, R2 sending out its update. This is where before we had a cross happening on this wire, right? All right, but we have a new rule. It's called split horizon. R2 learned about network X in step number 1 from R3. So it's not going to send an update down this interface because split horizon rule. It's only going to send it out this way. So you see here, it only sends it to R1. So what's the result then? We have R1 saying that to get to network X, it's 2 hops away through R2. I go here and I go here. It doesn't change anything with itself, and it doesn't change anything in R3. And you see here in the red, this is a change from the previous whiteboard because of the split horizon rule. All right, let's move on to step 4. R1 now has to send an update out. It believes that it's 2 hops away through R2 to get to network X, so it's going to send it out. Again, the split horizon rule. It's not going to send it out this interface because it learned it from R2. It's only going to send it here. So it keeps its entry that it had before, and now we have R3 believing that R1 is 3 hops away. So this is part of our solution, split horizon. It helps, but as you can see, it doesn't solve the problem. I still have routing loops going on. They're going to go on indefinitely. The need to have other tools to combat routing loops was actually brought up in the RFC that defined RIP. It said we need split horizon, but also we need a little change to it. We need poison reverse. And what that says is, split horizon says, if you're going to get an update about network X from router 3 to R2, when R2 sends its update out, it only sends it to R1. This is where it changes. It says, I will send an update this way as well as in this direction, but the update in this direction is going to have a metric that is infinite. So for RIP, it's going to be 16, saying this network is unreachable. And in the route update that goes over to R1 will have a metric of 2, as it normally would because it takes 2 hops to get there. So this is the addition with poison reverse. The other thing that was introduced in that RFC, it says whenever I send out triggered updates, and that's what we've been sending out in step 2 here, the metric is also going to be infinite. So they're going to use infinite there as well, saying that this network is unreachable, and we'll see that here. So let's see everything in action. Step 1 is going to have the same results that it did in the previous whiteboards here. Then we're going to make our change to our network. This interface is down. All right, the triggered update is the next thing to go out. Keep in mind, the metric's going to be infinite, and it goes out to R1 and R2. So here's the result on those 2 route tables, and I see no entries here on R3 because I know that it's down. All right, the third step, remembering that these are crossing again, because in step number 3 here, R2 is going to send its update out saying that 2 hops away, I have network X, and it's going to send that to router 1. But remember what I said, it's going to send to R3 a metric of 16 because of poison reverse. So let's look at that. It's going to send this packet out and this packet out with different metrics. A split second after, these 2 packets go out. All right, so the result is, in step 3, I'm going to see R1 with a route table of 2 hops to get to network X via R2, because that's better than the infinite or the impossibility that I had before. All right, and in that update, I sent an infinite metric here, so I'm going to adjust. I had no entry, now I have 16 hops, in other words, unreachable for network X via R2. In step 4, we see R1 sending an update of its own, and the reason for that, R2 just told it that the network is reachable via 2 hops, so it's going to send its update out this way to R3, saying the network is reachable in 3 hops. The changes will be made in the route table of R3 because 3 hops is better than it not being possible to reach it, right? The other part, remember our poison reverse, it's going to send an update to R2 as well with a metric of 16, saying it's unreachable. All right, it already said I don't even have it in my network table, and now you're telling me it's unreachable, so there'll be no change there. We're getting closer to a solution, but we still haven't made it. You still see the routing loop here. So we need more help, and that help comes in the form of a hold-down timer. The hold-down timer is a simple concept, but it's very powerful in fighting routing loops. And simply, this is what it is. If you're notified of a failed route from another router, for a specific period of time, you're going to ignore any new information about that route. Now, the default is for 3 updates. So if it's RIP, it's 90 seconds. IGRP is 270 seconds. And, we've seen in the past, the last few whiteboards that we've gone over, our problem was exactly that. We had lingering routes out here that simply weren't true anymore. And even though somebody changed their route table to say that it's not reachable any longer, another route would sneak in that says, oh, hey, I know where it is. Now with hold down timers, you're going to ignore that new information. Give that information time to die, and then by the time you start listening again, we should have convergence and be able to move forward. In this first step, we're going to see the same results that we did in the previous whiteboards. Then our network is going to go down. All right, here we're going to see the triggered updates from R3 with the metric of infinite. So those go out through here. Both R2 and R1 receive those. So here's the result. R1 and R2 have both infinite metrics in the route table. All right, just as before, we're going to cross right here. And in fact, this packet's going to get to R1 right after this one does. But note, it's right after. And because of that, both R3 and R1 are going to ignore the information in this packet. Remembering that R3, because of poison reverse, actually was receiving a metric of 16 anyway. But they're going to ignore that information. So now let's look at what we have. We have a metric, unreachable here, unreachable here. That poison reverse just provided our metric here, and now convergence in the network. Everybody knows that that network is down. R4 is never going to happen because R1 never believed this update here. So that's going to stay the same. And it's going to do that for a period of 3 updates. Now, if that network were to change somewhere else or to come back alive, that's when we'll see it added to the route tables. So now you know how distance vector protocols prevent routing loops. On to the last section of this nugget, and it's load balancing. If 2 paths present themselves with the same metric from one source to a destination, then load balancing can happen and will happen with distance vector protocols. So understand what load balancing is, though, to distance vector, because it's different in some other cases. It's talking about round robin. And so that means that I'll send one packet this way, one packet this way, one this way, one this way, and I'll continue so that I utilize both links. Now, where it can be not so effective is that I might wind up sending smaller packets here, telnet type traffic, and maybe HTTP traffic here. So I'm going to overutilize one over the other, but at least there is a form of load balancing happening. Now let's look at this too. What if I change one parameter? Here I had an Ethernet link. I want to change that to a WAN link and see what's going to happen in our scenario. Remember in our scenario above, whether this was a RIP metric or an IGRP metric, it would work the same. And because these are Ethernet links throughout, the possibility exists that IGRP might assign the same cost, right? But not here, because if I have a WAN link, it's definitely going to be slower than my Ethernet link, which the slowest possibility is 10 meg. So when that happens, IGRP is not going to see these 2 links as equal any longer, so load balancing isn't going to be there. But RIP will, because we're just talking about hop counts. It's still going to have 2 hop counts to the destination on that path and 2 here. But what's going to happen is, as I'm sending out my round robin traffic, what this link can handle, this slow pipe may not be able to. Let's say it's 56K. And what might result is a lot of queuing and buffering here at router 2. And you need to be aware of that. So if you're using RIP, equal paths might not mean that those pipes of that bandwidth associated with that link can handle the traffic that you're going to send to it. And it might give you some strange problems. There are limitations on the number of equal paths that can be load balanced depending on which distance vector protocol you're using. All right, in this nugget, we defined what the Bellman-Ford algorithm does and simply said it is used to search for the shortest path between a source and a destination. And then we looked at the metrics, its uses, and we identified that RIP uses hops and IGRP uses a composite metric. Then we looked at how updates are passed from router to router and the fact that they're sent out periodically. For RIP, it's 30 seconds. For IGRP, it's 90. And for other distance vector protocols, that will change as well. Then we saw the biggest problem facing routing protocols, and that is the routing loop, along with how we would battle that. The tools associated with the battle, split horizon, poison reverse, and hold down timers. These loop prevention techniques are probably the hardest thing for people to remember when it comes to distance vector protocols. So let me run you through an analogy that hopefully will aid in remembering this. All right, a quick overview of the diagram down here. This is me. I have a first line or first level supervisor. We're going to say that's Sandy. There's a second line above her. Now another first line for another department is Ray. And here we go with the analogy. I'm at work, okay? I get a call from my customer. It says, my local area network is down. I need you to leave, come out here and help me fix this network. So I'm going out on site. I let my immediate supervisor know. In turn, per protocol, she's going to try to let her boss know, which is my second line. Now, this individual isn't in at the time, so she's going to leave a voice message with him saying, Emilio is gone out to the customer site. This leaving of the voicemail is the exact same thing that would happen if I had a routed environment here. And this is that first update going out saying that this network is no longer available. In other words, I'm out of the office. All right, the reason that my boss is not in to receive this voice information is because he's in a meeting with Ray, which is another supervisor. Now, on my way out the door, as I'm leaving the building, I see Ray and I say, you know what? I'm going to need to meet with you today. How is 3 o'clock in the afternoon sound for you? Ray says, hey, that sounds great. Then he goes into his meeting. As he's in the meeting, the boss says, I need an answer to my question so that we can figure out what we're going to do going forward. Ray says, I'll have that answer as soon as I meet with Emilio at 3 o'clock. Then the boss says, hey, Emilio's not here. Sandy just told me. Ray says, I just saw him and I'm going to meet with him at 3 o'clock, so I'm sure he's here. So far, my analogy might sound a bit far-fetched, and the reason for that is it is exactly as it was when we talked about these loop prevention techniques. It's not something that happens often. In fact, it's very rare that loops would be caused by this instance, but it can happen and it does sometimes. So in this case, this would be a rare occasion. All right, so this time my boss is thinking that I am in the office and I'm going to meet with Ray at 3 o'clock. So he's got to be thinking, why did Sandy tell me that Emilio is gone? Up to this point, we've set up the potential for a loop. Now we're going to talk about loop prevention techniques here with Split Horizon. At this time, this is what is preventing this second line supervisor from calling my first line and saying, you know what, Emilio's not out of the office. In fact, he's with Ray. All right, so this is analogous to this router telling this router, I know you said this network was unreachable, but actually I can get there through here, and you see how that could cause a looped problem. The next thing was hold down timers. Now, this whole thing could have been avoided with the use of hold down timers. If this second line supervisor would not listen to anybody else, and that is Ray in this instance, about information concerning me. Had he not listened to that information for a certain period of time, there would be nothing to call my first line supervisor about. And then our last technique is Split Horizon with poison reverse. So it's a little bit of a twist on Split Horizon. It says, okay, I've got my hold down, so I'm not going to listen here. But just in case anything else did happen, or just to end all confusion, what I'm going to do is I am going to send an update back to Sandy once I receive my voice message and just talk to her and say, you know what, I've received your information and Emilio is gone, which is analogous to the infinity count on the metric for that specific network coming from this router back to the router that gave him the information on that network. And there you have one more vantage point on the loop prevention techniques that are available within distance vector protocols. Getting back to our list, we finished up our last section by discussing load balancing the way it's used in distance vector protocols, and that is the round-robin method. I hope this has been informative for you, and I'd like to thank you for viewing.